Gentlemen, let's begin the workshop. I'm Dr. Weiren Shi, and I'm honored to serve as the moderator of this workshop. I represent MRDC, and the Metal Industrial Research and Development Center. So I'm happy to be here, and we deeply committed to green energy transition, focusing on geothermal energy system integration. So today we have some mission to introduce something from subsurface to the electricity grid. So we have some discussion, some treasure speakers today, and let's welcome the first one, Mr. Anker Aurora from the Nikiso, please.
Morning. So from here. Morning, and thank you for the invite to Taiwan Geothermal Exposition. So great opportunity to present our showcase our capabilities. I've got my president with me. Fortunately, so I've requested Amir to kind of cover some corporate slides so you know where Nikiso is coming from, corporate details. Amir will take over from here. Amir. Yes, yes.
Well, good morning, everyone. I'm going to get closer to here. They can't hear very well, so I'll be their mic or their speaker. So, yeah, we come from Nikiso. Nikiso is a Japanese company, and about 8 years ago, they bought a big group in the U.S. that had a lot of products that fit into the organic ranking cycle application, pumps, expanders, heat exchangers. And we developed a strong team at the time to create basically a geothermal power generation solution that can be offered to many customers around the world. And we're very happy to be here, and we're going to give you a bit of an introduction of what we do. So we're about a $1.5 billion company, 8,000 employees. We have different type of businesses, but the biggest group is the CENIG, Clean Energy and Industrial Gases Group. So clean energy is part of our mission, our vision, and we strive and we believe in that because we're involved in cryogenic applications. And cryogenic application means liquid at very cold temperature. So we deal with hydrogen, liquid nitrogen, liquid oxygen. We're involved in many different applications with such equipment. So we are the largest cryogenic equipment manufacturer in the world in terms of size. We have the cryogenic pumps we have sold over the years. Many of them are actually in Taiwan, where you're importing LNG. They are on the cargo ship that comes here. They are in the terminal that provides you gas. So they work inside the tank at minus 160 all the time. So very reliable, high pressure, high power. We do have a purpose and a vision, which is leading the change to a healthier world. And I think this is why we all are here to talk about geothermal, because that's a renewable energy that can be used with very little impact to the environment. And we look forward to work with all of you in Taiwan to help our customers, or to help Taiwan make a difference on the environmental side. So I don't want to bore you with the history, but as I mentioned, in 2017, the cryogenic industry was acquired by Nikiso, and from there we developed a big group called Clean Energy and Industrial Gases, where the geothermal market is a focus market for us. So using our ORC technology and ORC experience with the engineers we have, we're very happy to be part of this drive around the world. So our businesses goes from aerospace, very exciting. We fill rockets that goes up in the air. We are working on trying to fill rockets while in the air. And and using our equipment, pumping equipment. Most of the vessels that have dual engines use our equipment to run on gas. So LNG fuel vessels, for instance. On energy sector, we do a lot of power generation projects on islands. So we do regasification of the LNG and work with the engine or the power generation companies. On industrial gases, this is the base of our history. We started basically with oxygen and liquid oxygen, liquid nitrogen. We had a lot of work during COVID because there was a lot of need for oxygen, so we were part of that essential business that kept producing a lot of stuff to fight COVID. On marine, it's very big business for us. As I said, on LNG carriers, on propane carriers, on LPG carriers, and even hydrogen. So there was a lot of experimental with hydrogen to run basically ships and buses with hydrogen, because hydrogen with fuel cells have basically water as a byproduct. So it's very environmental friendly, but hydrogen is at minus 253 degrees Celsius. So very difficult molecule to manage. And we're involved in the transportation. We build a lot of fuel stations around the world that uses hydrogen as a liquid hydrogen as a fuel. So that's also a difficult product to make. So we're always at the forefront of technology, and ORC has been in our history. I started my career 40 years ago, and I was involved in geothermal application or projects in California at the time. Through the company that I worked for, supplied many prototypes using ORC technology. And we were even using ORC in Hawaii, utilizing the temperature difference between the top surface and the bottom surface of the sea, creating basically power generation for that cycle. I'm not here, but they have to hear me. They can't hear me. You guys can hear me over there? Yeah, very good. Okay. So we have 6 divisions. The pump divisions is responsible, or turbo expander division also is responsible, which I lead, is responsible for the geothermal applications. The heat exchanger division, and then the process division that we have, and the fueling solutions and the NESP, where we can do basically ORC inclusive of a turnkey approach. We can do the balance of the plant, including the operation and maintenance, and services division that focuses on supporting our customers around the world. So that's how we're basically organized. We're present around the world. Here in Taiwan, we have a long-standing partnership with TIGC. We have chairs with TIGC, so we're very close and have to embrace the same culture, the same focus on the market. They're very essential to what we're trying to do here in Taiwan to push this geothermal application around Taiwan using the resources that you guys have. Our experience really on ORC and turbo expander, as I said, I have 40 years experience, and a lot of the work, the people, the engineering people have, that work for us have really built many geothermal plant operated and maintained many of them. Combined experience of 380 years plus. We keep adding resources as we grow our business on this side of the application. So we have a lot of experience, and we know how to do these things within the range of our turbo expanders and equipment range. We normally do not buy and assemble a plant without using our equipment. So we are an integrator from within. So we have equipment and we have the process on our side. I'm going to let Anchor say something because I think he came here to present. So I'll let you go from here. So thank you. And if you have any questions later, we can answer. Thank you.
Thank you, May. I'll stand more in the center. Yeah. So here we cover basically the EPCM solution. We offer a single point responsibility for the ORC. For Taiwan, in the case of Taiwan, anything ground up without construction, we offer a complete solution, including power evacuation. So which means your power distribution, right up to the power distribution, we can offer a complete EPCM solution. We've got a strategic joint venture with Egisim. Egisim's been in business for over 30 years and has been managing all the geothermal plants. So we've got a very good relationship and joint venture with Egisim to push the ORC solution, including the balance of plant. So the responsibilities individually, if you look at on the integrated capabilities, we are more focused on the technology, the ORC equipment, and all that side of things. And Egisim is more uh, uh, working on the balance of plant, electrification, automation, power evacuation, and things like that. A little bit about Egisim. Egisim is a very trusted and a partner of Nikiso. So about 30 plus years we have experience together. We've done 2,000 plus projects. A lot of us in the past have also been involved in our various positions with Egisim. So we offer a complete, comprehensive solution. The range in ORC, we start as low as half a megawatt to as high as 25 megawatt single train. We can double end it, which means we can do a 50 megawatt unit as well, single train. We are a radial inflow turbine, so we are a radial inflow turbo expander. I'll explain in a few slides. The temperature range, which is quite suited for Taiwan, in this case is between 80 degrees C onwards to 250 degrees. So we are a products company and we are a systems or a solutions company. So we have integrated both. We manufacture a lot of products. So within ORC, we manufacture almost 80% of the products in-house. So it's not subcontracted. We manufacture all that in-house, which is pumps, heat exchangers, expanders, and then we try to integrate that as a system, as a project for a client together. So a lot of the blue, I don't have to explain to you what a geothermal plant is, but a lot of the blue rings, if you like, those products are manufactured in-house within the Nikiso capability within Murrieta or California as our hub for all the main manufacturing, and then we are spread out around the world in 22 different countries. So we manufacture equipment everywhere. We do provide engineering, equipment, feed, HAZOP, so we provide a normal EPC or project management cycle, if you like, right from concept select to the feed or the FID. So we provide a complete package over here. Mechanical design, civil designs, we provide a complete scope on the mechanical design for the whole ORC plant. So anything ground up, we provide right up to the power evacuation. We will conduct or be part of the hazards, HAZOP. We'll offer a RAM report. The plants currently within Nikiso Egisim sort of portfolio are running around 97-98% availability. Electrical and automation. So as I explained, that is more process handled by Egisim, and that's manufactured also in-house. So Egisim is part of the Siemens manufacturing group. So Siemens supports, or they can manufacture Siemens panels, OE panels, and so they are manufacturing in Munich, in Germany, and also in Turkey. So we manufacture for all the automation and electrical stuff. This is manufacturing in-house, or just a workshop. Few projects that Egisim has conducted over the years. So this is in Turkey as well. In Limgaz, this is about 13.4 megawatt. Why I kind of used that reference was because of the height. There was no space on the project. So if you look around, there's not too much of a footprint. So we had to really adjust and motorize according to the requirement on this particular. It's quite high as well. And this was completed around 14 to 15 months from the date of award. So well within the duration. Osman power plant again in Turkey. This was also completed well and truly within the time frame, and this was also having the SCADA infrastructure automation kind of involved at that point. Or 22 megawatt. This was in collaboration Egisim did with Toyota, Toshiba, and Egisim, so there was a joint kind of collaboration there. And this was about 5 megawatt roughly, and this was in Ethiopia. And here we also had to take a responsibility of civil works. So the Ethiopia, there were some issues, there were some local issues, political issues also. However, we had to manage the civil contractors also. And then this is a waste heat recovery, which is in Australia at the moment. It's about 3 megawatt roughly unit, and it's a very unique project. It's basically taking the energy from the solar panels in the daytime, and then we are using the water, the heated water, in the nighttime to recover or run the ORC. I'll cover that in the ORC presentation in a short of time. A little bit about turbo expanders. So I'll just touch a little bit on details. So we've got a lot of history on the turbo expanders. We've got 50 plus years of experience on variable inlet guided vanes or turbo expander designs within the group. A lot of papers have been written by the team that is heading the division. We call it NEAT, so Nikiso Expander Application Technology. So the expander team is doing a lot of papers. Dr. Reza, Dr. Beruz, the team has headed a lot of these technical papers and patents over the years. We've got so it's an API 617, it's an integral gear design, so it's a smaller size. So it's all made on the, it's all basically assembled around the gear, the boom gear. There are 3 types of different technologies on the turbo expander. You have axial turbine, which is quite widely used in geothermal. You have radial outflow, and then you have a radial inflow. So we are, within Nikiso, are basically radial inflow turbine. So the flow end is 90 degree, and then we pass on axial load out, or axial flow out from there. And this is also catering our hydrocarbon needs. So a lot of hydrocarbon needs, we are managing with the radial inflow turbine much better. If there are any variations, we can manage that within the pressure, temperature of the reservoir. If there is any change or any design criteria for minimum, maximum, it's far easier to handle in the radial inflow than in axial flow unit. So these are variable inlet guided vane units. They are basically externally actuated, so there's no galling. It's on the expander wheel. They're externally actuated. On the design side, using HYSYS, all the manufacturers are using more or less similar software. So we are on the design point, more or less everybody's similar on the efficiency side. However, the moment you move away from the design point, that's where you see the variation. So you see a lot of variation if the reservoir pressure is going down, or the flow is going down, or the temperature effect. So you can manage those with the inlet guide. Just conscious of the time, I'll just pass on to something unique. So we also provide island mode. So fortunately, because of the variable inlet guide vane design, we can go into let's say a risk or an island mode in case there's an earthquake. And so this is a profile of an earthquake in Turkey. So 10:48, I don't think you can see it, but that's about 10:48 a.m. and then around 11 a.m. you can see it ramping up. So this is, it goes to an island mode, which means it recircs its power. So it sees a hazard, the ORC plant automatically understands it produces enough power, captive power, to run the ORC plant only in safe mode. And we can continue in safe mode for a few days to a week maximum maybe, before you can you go into you diagnose the problem. If it's a major problem, then you go. But we can ramp it up back onto this without shutting it down. So we don't have to do those expensive 2-hour shutdowns and all that side. Turbo expander range, so limited by the gearbox more or less design, which is about 33 megawatt roughly. But the power range is, we can go as small as 100 kilowatt to as large as 25 megawatt, which is single train. So if you double end it, then of course you can go up to 50 megawatt. But around the world, what we are seeing more and more is, the inquiries that we are seeing is redundancy is coming up. So people are more looking at redundancy. So 25 megawatt is kind of the standard. Service locations, and we are spread across the globe, of course, with service hubs, major service hubs everywhere. And here we are serviced by Nikiso with Steve's team here. So we have a local service presence. It's our presence for Turbo team is all trained here and is available. We're also working on modernization of the ORC plant. So we come, because of the oil and gas and the hydrogen and all the other background, we are now working on improving the modernization so that your implementation of the install time kind of reduces down. So we are working on a project internally, and we are making it as much as possible skid-based and waterizing it. Because Amil touched a little bit about hydrogen, so we are also producing hydrogen electrolyzers together as packager. So, and the hydrogen distribution stations. So geothermal is a great fit. It's when hydrogen does take off. At that point, geothermal is a great fit for the hydrogen because it provides that green energy. We do the hydrogen electrolyzer. We can also do the distribution stations, which is here. So we provide all the liquefaction distribution for hydrogen. So we are looking at end-to-end game, end-to-end solution on this. And we are working very hard on that in US at the moment. NCG mitigation, this is another stream which is coming up. With geothermal, you have a lot of emission coming from the ground, so it's very hard to control those NCGs. So we are now working, it's confidential, but we are working on a few projects where we are looking at the NCG mitigation by purifying it to beverage grade or a commercial grade CO2 out of it. So because we have the CO2 heritage, which is back in Cryotech days, which company we own in Germany, which started in 1880, so it's very, very old heritage that we have, that we are actually working on the projects where we can take the emissions out, clean it up, scrub everything, or amine it, basically take the H2S and everything out, and produce a commercial grade CO2 for the growers. Our biggest strength, we are local. So TIGC is our biggest strength here if you ask me what is our best strength against all our competition at the moment, so I would say we are local. We have a local presence ourselves. We have been in 38 years, thanks to Steve. So we are part of a group company, TIGC, which is part of Nikiso as a group company, and we are able to service locally. Plus our core team, like Amir touched, which is about 380 years of experience. Amir used 40 years of your experience added last night on the slide. So we have 380 years of experience. We have a lot of experience with ORC. Including our chairman, Peter Wagner. He comes from the ORC background as well. So Peter Wagner is the chairman, but he's also the geothermal man. Why Nikiso? We've been in business for 70 years. We design, manufacture, deliver, service, operate our own equipment. So we offer complete package onto the equipment. We do not get into a business line if we are not able to service that business line in the country. So our progress is slow into countries. We are very skeptical. We choose our battles where we have to go, but we are very careful where we need to be. And so Taiwan, we are committed to it, and we are here with Steve to support the ORC business. These are our sheshe to all of you. Thank you. And I just wanted to all stakeholders as well, have a wonderful conference. And I met David yesterday, and so no, thank you, all of you. Have a nice conference. These are our contact details. And that's all. Thank you.
Thank you, Mr. Anchor. We hope we have the chance to anchor with Nikiso in the future. So next song, I have to apologize first because we cannot turn up the volume here. We have a lot of CPC pro here. So next song, we welcome the Mr. Thorstein. Is that correct? Yeah. Okay, great. Mr. Thorstein to bring us the best practice in preparing a geothermal project. Welcome.
Good morning. You hear me well enough? I got the topic to talk about best practice in preparing a geothermal project. This has kind of been the agenda throughout yesterday on what methods to use to develop geothermal. I come from Kowi in Iceland. My background is in geothermal for the past 30 years. And including preparing geothermal projects and just working in the expansion of projects, operation enhancement and so on. So there are quite many useful written material about how to use best practice in preparing a geothermal project. Myself, I kind of like the one from ESMA. These are the World Bank guidelines. But in addition, yeah, there's a lot of written material which is good to follow. Just here a little bit about the introduction. What does it include to prepare this? A little bit my take here is to understand clearly from the beginning who is doing what is to be done, why we are doing this, and where in the process it's supposed to be done. And this is about survey studies, exploration drillings, power plant facilities. I guess a theme which we have already heard a lot about yesterday and just generally. You saw this picture from baseload yesterday. It doesn't really have anything to do with the preparation of the plant, but it shows a little bit about how to manage the operation during a situation like this. This was taken last year in Iceland. Yeah, there is the power plant and then there is the Blue Lagoon there as well. So people were actually bathing during the rupture. A little bit about the different type of resources, and there may be different paths to prepare those projects depending on if these are low to medium temperatures. Is the plan to develop a direct use project, or is the plan to develop a power project? Different paths as well. The cost and the risk is kind of the most important thing. Starting early, just carefully spending as little money as possible and do all the best to mitigate risk involved. It would be nice just to start somewhere around here, go directly to the drilling phase. I guess this has been done too many times, a lot of funds spent, and projects die, and probably as well the geothermal industry is a little bit hurt because of lack of success. And about the finance part, the developer generally needs to have some equity to start his activities. Either these are coming from his own pocket or grants. Normally the banks are not really willing to jump in until they know what the risk is less, so to speak. There are risk mitigation funds which are deeply involved in these activities. East Africa is the GRMF. In Asia, I guess ATP, World Bank, and many others. This is borrowed from the ESMA guidelines as well, how to prepare for these activities. A lot of, let's say, experts are supposed to be involved, legal, technical, finance, science in terms of geology. And the World Bank guideline was kind of missing this one here, which is cooperation. So to have a successful set of cooperation between partners is one of the most important. But again, to have sure who is doing what, when, why, and so on. In Iceland, we do a lot of direct use projects as well, so it's kind of the same circle. And of course, cooperation is just as important for this scenario. My background is mechanical engineering. I always try to be a little bit careful when talking about surface studies or something to do with the reservoir, so I'll just go quickly through this. Every geothermal system is unique, and these are the variables which are involved. So studies on each of those variables are important part of the preparation. Types of surface studies necessary, at least if following the well-point guidelines or the SMAP guidelines. I may be kind of repeating myself over and over, but I guess never enough. About the timeline, again, it's about who, when, why, and what. But generally, this may take from 6 months up to 2 years, depending on what is necessary to be done, which is a little bit different between countries, actually. Is there Asia study necessary, or like in Indonesia, for example, the process a little bit less complicated in that sense? Sorry for my lack of knowledge here for Taiwan. I actually don't know the process, but it would be nice to figure out how this works. In the end, this is kind of the pre-feasibility report, which will be generated. A huge milestone along the way, and this is what it will include. It will definitely be the guideline for the next step, and this can be presented to the lenders, to the banks, risk mitigation funds, so on. And most important, this is the guideline for the owner to understand if to move forward or if to stop. Now into the exploration. I get the feeling sometimes here in Taiwan that the developers want to jump directly into the exploration and skip the pre-feasibility or kind of the most important part of the risk mitigation. Just hear a little bit about the wells which are necessary at some point. The decision to drill small diameter research wells, thermal gradient wells, so on. Water supply is an important part of the exploration. Injection wells. The wells are different depending on if there is high enthalpy or low enthalpy. The equipment is different as well, depending on which process to follow. And even for ES drilling projects, which we heard a lot about yesterday, there is another scenario, completely different. A little bit again about the wells, standard wells, depending on how aggressively the developer wants to start. Slim wells can be a consideration as well. those slim wells will most likely not be a part of the exploitation if it comes there. So this be like a lost cost, while standard wells will definitely be a part of the further utilization, given that there will be any further utilization. And again, there are different types of wells. Slim wells, well, perhaps slim wells are good enough for very small capacity projects like just 1, 2, 3 megawatts, something in that range. So this may be an alternative which should be considered. Most common in Iceland is standard size with a 10-inch master valve sitting on top. Large wells are often drilled as a part of the exploitation, not the exploration. About the enhanced geothermal systems, we can very well understand from yesterday that a lot of funds are coming into this part of geothermal, and I'm pretty sure that these are not coming from the pockets of the developers. This is probably some rich risk-taking investors who are jumping on board. So for the, let's say, less income countries, at least there is no risk mitigation facility for years. Maybe, yeah, before I move forward, this is kind of the way that Icelandic companies have been doing. I would very much like to hear the opinions from other countries. There may be different approach. For example, in New Zealand, USA, Indonesia, or whatever we are. So I look forward to this discussion. This is just a picture taken from Iceland, as most of the pictures in my presentation. This setup you all know very well, but how important it is to make sure that all tests are done, and it can be demonstrated that the design project can actually sustain for the end of life, let's say 20 to 40 years, and can be the base load for a long time. About codes, in Iceland at least, we kind of like to follow the New Zealand code in developing our systems. In Africa, there is the African Union Code of Practice. It's probably a copy of the New Zealand code, and I guess in other countries we are benefiting from all the good things developed in New Zealand. It's about how to design your well, how to implement the drilling, well testing best practices, well operation, abandonment, and just quite many of the New Zealand standards are used all over. They may be called Icelandic New Zealand standards or just New Zealand standards. COWI has for quite many years been the technical part of the GearMed risk mitigation, and we are always using this kind of as our guideline. So the feasibility report to be generated following the I'm not going to read all which is stated there, but it gives you the guideline for what to do next. And this is the report which the financial institutions are going to look into. So make this as well, as good as possible, and this will be the path forward for a successful project, let's say for the 20 to 40 years ahead. Here last about the geothermal power plants. We heard about overseas units here just earlier. You can call this binary. There are flash systems like single flash, dual flash, or whatever. And then there are back pressure units, which are actually quite common in the initial development. And this is kind of a cheap solution as well, possibly to demonstrate that there is a sustainable project. The most recent power plant in Iceland is just few megawatts, and that's a back pressure unit. And yeah. These are the typical cycle for flash. I'm not going to go deeply into this. I though want to mention about the condenser. There are two ways to design the condenser. One is direct contact condenser, which I guess the most common one in the world. In Iceland, at least now the most common one are surface contact condensers, meaning kind of shell and tube heat exchangers. And why is this done in Iceland? Yeah, it's to use the cooling application as the heat resource to heat our homes. And this way you can easily collect the non-condensable gases from the stream as well, to be utilized for scaling, mitigation, or just for the carbon credits, which are quite important, at least in Europe. You get the pure condensate, which is a valuable stream as well. But again, to decide on where to go is very important in the beginning. Iceland kind of decided to go that way, and it has been kind of a success. So, important decisions in the beginning. Just about the timeline. This is taken from a plant in Iceland commissioned in 2018. 3 years from decision to commissioning. And that's all for me. Thank you.
Okay, thank you, Mr. Thorsten. Is there a note? Hello? Okay.
Oh yeah, sorry.
I was so excited when I saw your name, the Almighty Thor. Yeah, I'm a big fan of Marvel. Okay, so next on we have Mr. Let's see. Oh, Mr. Jack C. Wiley from OSA. Yeah, so he will guide us through the optimization of the geothermal power plant. Please welcome Mr. Lee.
Hello everyone, my name is Jeff, and Jack is over here, and I'm work in OSA and responsible for geothermal sector. Therefore, Jack would like us to share the experience and some insight with you for our development in Taiwan. Okay, so okay, thanks. Okay, so OSA is a system integrator and also equipment provider for geothermal. And not only geothermal, we also do the biogas and also provide the instrument and remote monitoring. Okay, but since we are going to we are a local service provider, therefore I would like to share the content in Chinese. 那当我们在做整个第二开发的时候，其实很多业界的先进也告诉我们有一些很完整的步骤。那这每一个步骤呢，其实都很关键。那从最一开始的初步探勘，整个大范围的探勘，到一个比较具体的细部探勘，包含3G 的测试、地表的测试。有了这些资料，我们就可以取得一个初步的可行性分析。那这个过程其实很重要，因为若没有这些资料，就去挖一个探勘井或做整个暗场的探勘，其实风险是很高的。那因此初步可行性分析之后，再来决定是不是在这个区域来做探测井。那有了探测井的资料，我们就可以取得地底下的地质资料，取得水温资料。那有了这个资料来做一个正式的可行性分析。那这样的分析之后，我们就可以进到暗场的开发。那在我们公司所提供的是在钻井之后，我们有提供 Novomed 的沉水棒，可以来提升整个产能。那以及在电厂的设计、电厂的建制，还有发电机，我们有 Orcan， 还有我们公司自己做暗场的设计跟规划。那最后的投产，那其实这整个流程其实对台湾的开发商来讲，其实蛮辛苦的，因为有很多需要整合不同的专业，需要整合不同的技术，有很多不同的供应商。所以怎么样去成功开发一个地热，其实很关键的是需要有一个完整的不同的领域的专业的团队一起组成。所以我们公司除了在最下面的4项有提供这些设备跟服务之外，很关键的我们也持续在跟业界不同的专业的团队一起整合，希望针对整个地热的开发有一个完整的团队来服务这个产业。那有了专业的团队以及这样的开发的步骤，整个开发的风险其实就可以去大幅度的降低。那接下来我想跟各位分享一点关于整个如何在提升产能的部分。因为前面其实有专业的厂商。那第一个，其实台湾的地热最大的问题，尤其东部在东部遇到的问题就是OK 那个井挖完了可以自由，可是那个水量不足以能够支撑这个暗场的规模化，所以那这是第一个问题。那第二个问题是结构的问题很严重，我想业内的朋友都知道结构问题很严重。那为什么结构？结构就是因为当地底的水它里面有很多的矿物质，很多的碳酸根离子这些东西压力当它慢慢降低之后，它就会开始释放二氧化碳，那里面的水的 pH 值就开始发生变化，那就开始结构。所以当这个第二生产的时候，你如果用自由的方式去生产，那就绝对避免不了结构的问题。所以在国外，尤其在除了那种高温的环境的国家，像土耳其，他们是高温第二水，那他们就导入蛮多 ESP 的。那因为 ESP 有两个最大好处，第一个是提升跟稳定产能，那第二个是保持压力。那这两个因素都对于暗场的规模化跟它的稳定生产都非常的关键。因为一旦结构，基本上这个厂可能每3个月或2个月就要停机，然后去维修。所以我们在尤其台湾东部的暗场，其实我们都非常建议我们的客户一定要安装 ESP。那不管自涌量好或不好，就算再好，基本上它压力还是会掉，那还是会有结构的问题。那 ESP 到底要怎么选？很多人就会说，那这个第一个问题是多少钱？第二个问题可以用多久？那其实这两个问题之前，我想跟大家分享 ESP 的选型的一些关键考量。那第一个 ESP 的关键，第一个是要第二生产，它其实跟石油不同，石油井小小一口，它的经济产值就很高，但是第二井它一定要有大量的水跟很好的温度，所以在第一个 ESP 它需要有很好的流量。那 流量基本上就是，但同时第二又有井的大小的限制，所以怎么在同样的 size 里面去选择一个能够提供最大流量的泵，那这是第一个选择的因素。那除了流量之外，它的流量稳定性也很重要。那流量稳定性我待会再来说明。那第二个是，当大流量代表通常泵要么就是旋转的高、旋转的快，或者是泵叶轮大，那它要做的功就多，所以这样耗电量往往就会也伴随着提升。所以怎么在整个系统，包含水泵、包含在马达，还有整个系统的设计，它的效率需要高，那这也是很重要的因素。否则，ESP 的耗电量其实也蛮惊人的。我看大跟小，可能从100 kW 到200-300 kW，按照不同的井的状况不同，不同的 PI 它有不同的耗电状况。好，那第三个是第二我们都希望它温度很高，可是，在电子元件里面最怕的就是高温，所以整个马达还有整个电线的设计、绝缘的设计就非常的重要，它能不能耐高温？尤其像如果去了解ESP 容易损坏的地方，特别是电缆的接头，很多是电缆会在底下接头，那这地方就很容易是会有问题的。那怎么去解决这个耐高温的问题就很关键。那再来，有了这样的设备，在我们在看的很多案例当中，有一个是很关键的，每一口井它的 PI 都不同，它每一口井的井底压力也都不同。可是我们刚刚讲到结构其实跟压力有很大的关系，所以这个 ESP 怎么样设计在一个整个电场不同的节点当中，我去考量所有节点所需要的压力，那我让我的 ESP 能够提供一个符合我这个电场所需要的压力，这是这个 ESP 我想是很重要的一个设计因素。所以正确的扬尘的需求跟正确的井头压力的规划是 ESP 设计的很关键，否则有流量，但是在 ORC 那边或在热交换器那边可能就会出问题。OK， 好，那除了这样之外呢，还有一个是，因为第二井里面它可能随着时间或随着一些因素，它里面的温度可能有些微变化，或者它压力可能有些微变化，或是电厂有一些它的需求，所以这个 ESP 怎么有足够的操作范围来应对我们所希望的扬尘的范围、压力的范围，或是流量的范围，这也是在设计 ESP 的时候需要考量的。那刚刚这些其实它都需要一个很关键的因素，就是它需要一个完整的模拟分析软体，从压力、流体，还有不同的气体成分分析，包含每一个设备它的能力，这些一个综合分析的软体来针对每一个暗场的状况，在设计的时候，我们能够去提供一个完整的分析的规划，来确认这个 ESP 的性能。那以及在 ESP 的安装深度，这也是需要考量的。深度如果不对，那 ESP 的运转可能会出问题。如果深度太深，那里面的管损可能会太多。所以怎么去找到一个最佳化的安装深度，也是提升效率的关键。那除了这些之外呢，ESP 它基本上这种电器的东西，它面对耐高温，它一定有它的寿命的问题。所以怎么样有一个很好的当地的服务维修团队去跟原厂借接，这也是去维护整个 ESP 的运转效率的一个关键。好，那这是关于 ESP 的在设计的时候的一些很重要的考量。那接下来我们想介绍一下我们所代理的 Novomap。那 Novomap 是一家专门提供，它只做一项服务，就是做地热或是油气井的这种人工举升的设备，也就是 ESP。那它在1991年成立，那目前在全球32个国家有提供他们的服务，那全球有5000多个员工。那它也是全世界最早去投入地热专用的 ESP 的公司。那它的品牌针对地热品牌是 Geyser 这个品牌。那它在全世界除了像美国、然后印尼这些火山型的国家之外，它全世界用最多 ESP 的目前是在土耳其，因为它的条件跟台湾比较相似，是高温地热水，所以它在土耳其跟冰岛的市占率有达到80%，都是用他们的 ESP。那接下来介绍一下整个系统，我想有些人可能知道，有些人可能还不是那么熟悉。那在 ESP 的系统里面， 分为上跟下两个部分，有地表设备跟井底的设备。那如果先来介绍井底的设备，我这边是生产管，那下面这边就是我们刚刚所提到的，要确定它安装深度是多少。那从这个安装深度这一串，它其实有不同的元件来组成。最上面这边是 ESP 的水泵，那在下来这边有 ESP 水泵的这个水的入口，那以及在下面呢是一个轴封一个保护器，那这个保护器是为了对接水泵跟马达中间的一个缓冲。那下面就是马达那在马达最下面有一个，通常会安装一个 sensor， 那这 sensor 就是可以去量测井底的温度，量测井底的压力以及出口这个泵的出口压力这些数据以及流量。那这些数据其实很关键，因为如果没有这些数据，其实我不知道我在跑什么，我也不知道到底真实的状况是什么。那我们刚刚提到，怎么样去设计一个真正正确的适合的 ESP 水泵呢？其实就关键在于这些不同的组件的配搭。例如说，水泵里面到底需要每一个这个，因为通常会有不同的大小，那每一个大小每一个型号，它是一个多 stage 多级组成的水泵，到底要几个 stage？多了当然多一点 buffer OK， 但是多了它可能就会多一点耗电，所以怎么在当中取得平衡，其实就在这边的设计。那再来就是关于马达，因为整个系统的效率其实很大的一部分取决于马达的效率。那在 ESP 里面通常有两种马达，一种是传统的感应式马达，那另外一个是永磁马达。那我们这边可以看到，这边有两条曲线，上面绿色的是 PMM 是永磁马达，那红色的是感应式马达。那我们可以看到，当永磁马达它其实不论在负载是多少的时候，它其实它的效率都是高过于感应式马达。特别当我如果负载跑得比较低的时候，它的效率其实差异非常大。那即便跑到比较高负载的时候，它的效率其实还差蛮多的。那根据我们之前原厂的统计，他们这两者之间它的耗电差异大概是25%到28%。那这算一算，其实对一个第二电厂的营运，那其实影响是蛮大的。那在 Normal ESP 它有几个它的关键设计的节点。第一个，它耐高温最多可以到250度。那它最大的水泵流量是这应该是900 TPH。那安装深度是6公里。那整个 ESP 都是客制化，它按照每一口井的需求做客制化。那当然它的材质它需要耐盐碱，那材质也需要能够通过如果有一些细颗粒它都是会有不同的设计可以去应对。那最重要的是它这样设计完来维持井的压力。那这是我们在台湾的一个案场的一个实际的时机。它的也有一个东部案场，它的产能从一开始自涌的状况下10到20吨，到安装完之后，它稳定跑120吨的产能。好，那接下来有了流量之后，很关键的就是发电机的选择。那我想有很多不同的发电机。那发电机 ORC 发电机呢，一些很重要的，第一个当然它的稼动力要高，它的效率要高。那怎么去降低整个它的，比如说散热水箱，或是散热水塔，或是循环棒的功耗，来达到它的高效率。那我们所代理的 Orkan 这家公司，它从德国来，那德国从过去有很多的余热回收，所以因为它的应用很多，所以它从一个模组化起家。那模组化的好处，第一个是它可以很快速的部署，它不需要现场组装，因为那些设计图都好了，所以业主可以在订购的当中先做管线的预制。那机组到了 ，plug and play 就可以上线。当然还是要调试啊，但是它相对在暗场组装的时间跟所需要的人力是少很多的。那模组化的第二个好处是，它像 Orkan 他们基本上也算是一个这种整合商，他们设计好之后，他们向全世界提供最好的品质的供应商来购买他们的不同的零件。 那这些零件都是大量生产标准化的，所以这样的零件的好处，第一个它的经过验证，所以它的可靠性高。那第二个，在需要维修的时候，它能够维修备品的准备相对的交期也快。那 Orkin 的设计，它除了标准化，它不只是做 skid type， 它把整个都尽量整合到一个货柜里面。像右边这个图，它是一个40尺的货柜，两边是 ACC， 中间是 ORC 的核心的元件。哦，那它这个基础40尺货柜的机组，它的设计发电量是200 k 瓦，所以它在运输上，同时也非常的方便。那 Orkin 这家公司呢，我们刚刚讲过是从德国起家，那它是一个从大学的教授跟当地的政府还有一些企业所合资创立的。那2008年成立，在全球170个专利，算是如果以 ORC 来讲，相对来说算是一个新创。但是它在小型模组化的 ORC 里面，它总共累计销售了超过600套的机组，它是小型模组化里面全世界销售第1名的厂商。那它平均的架动率跑出来是95%。那 Orkin 呢，它除了提供我们刚刚讲的这种40尺货柜200千瓦之外，那它针对地热，它也提出一个，它已经提供一个1500到2000千瓦，1.5 МW 到2 МW 的单一机组。那这机组刚好非常的适合台湾东部的案场，因为我们目前的案场规模偏小，都是单一口径的设计。那以这个温度我们算下来，刚好一个这个 EPU 1500、2000这个机组刚好很适合。它跑的区间大概可以从1 МW 跑到1.7 МW， 净发电量从1 МW 跑到1.7 МW 左右。那它所有的这些核心的元件都是它这里面是不同的元件，那它把它整合在货柜里面，所以它运送来的时候就方便连接，不需要在案场去现地组装。那这是我们在金轮的一个案场，那这个案子是我们有点为我们的业主做一个小型的客制化，把一个2000千瓦的机组把3个并到一个货柜里面，那这设备都已经到案场了。好，那最后这边再跟各位介绍一下我们公司的服务。我们除了中间的这个沉水泵之外，那右边的发电机之外，其实我们也跟意大利的Steam 这家公司有合作。那 Steam 是一家第2开发顾问公司，他们提供 end-to-end 全端的服务。从前面如果例如说案场有一些地调的资料，他们也可以做 third party 的判读。那他们也可以做专井的顾问服务，甚至如果有需要做设备选型，他们也可以提供顾问来帮助业主去分析不同的厂商的优缺点，来给出建议。所以他们的服务其实范围很广，从不同的节点他们都可以来提供服务。你可以如果有需要，可以邀请他们 on site 或是远端按小时计费，他们都是可以提供建议的。好，那以上是我们公司的一些介绍，谢谢。
Thank you, Mr. Jeff. Although I want to have our whole schedule on time, but if you have any question about the speech, please feel free to raise your hand and we will deliver the microphone to you. So next song is the OMET. But it's a pity that Mr. Shavit cannot be here, so we have a pre-recorded video for him, and the topic will be from Hawaii to Taiwan, geothermal innovation, reliance and community synergy. Okay, let's play the video.
Good morning, everyone. First, I want to take a moment to thank the organizer for arranging such an excellent professional conference. It's both an honor and privilege to participate in this annual gathering for the 4th time. Unfortunately, due to unforeseen personal reasons, I unable to attend the conference in person. I'm excited to share with you today a topic that is focusing on how geothermal energy can drive innovation, resiliency, and synergy between communities and technology. Today, I want to take you on a journey from a wide geothermal transformation over the last few decades to Taiwan's future potential in tapping into its renewable energy resources. Imagine a place where energy costs are skyrocketing because of dependency on imported oil, even though there is a huge natural power from Earth beneath their feet. That was Hawaii in the 1980s before they began investing in geothermal infrastructure. Now, Hawaii is powering thousands of homes, significantly cutting its reliance on oil and preserving its environment, all through geothermal innovation. This story is not just Hawaii. It's a blueprint for Taiwan and other regions looking to transition to renewable energy while facing similar challenges. The Puna Geothermal Venture (PGV), located on Hawaii Big Island, demonstrates the power of geothermal energy to transform local community. Before PGV, Hawaii relied on imported oil for 80% of its electricity, making energy costs among the highest in the country. Today, thanks to PGV, Hawaii powered 25,000 homes, reduced oil use by 190,000 barrels annually, and uses sustainable practice to protect the environment. PGV is more than a power plant. It's a successful story that shows how technology resiliencies and collaboration with native Hawaiian community can unlock clean energy potential while respecting cultural traditions. Hawaii versus Taiwan similarity and differences. When we compare Hawaii and Taiwan, we see many similarities. Both are islands striving for energy independence, both facing challenges like limited land, volcanic terrain, and public resistance to large-scale projects. However, there are some key differences. Taiwan energy market is larger and support more industrial application, whereas Hawaii primarily focus on providing power to local community. Taiwan also faced unique challenges like balancing energy independence with national security issues. While Taiwan is still transitioning to geothermal energy, Hawaii offers lessons and insight into how resilience and collaboration can make this transition a success. Regulation, Hawaii versus Taiwan. Regulation are key to driving renewable energy adoption. Hawaii has strict regulation designed to protect air, water, and resources while meeting ambitious goals like achieving 100% renewable energy by 2045. Taiwan, on the other hand, has adopted a long-term geothermal strategy under its Renewable Energy Development Act, with incentives like feed-in tariff aiming for 1.2 gigawatt geothermal capacity by 2030. Despite the challenges like land restriction and public opposition, Taiwan can learn from Hawaii's ability to align strong regulation with technological innovation. Ormat stepped in and changed the story of Hawaii. By turning Hawaii volcanic energy into clean, reliable power, Ormat built a model of sustainability and community collaboration that guide other regions like Taiwan towards similar success. Ormat is proud to be a leading geothermal energy provider with over 60 years of experience, 1.7 gigawatt of renewable own and operate globally, and proven history of delivering reliable, clean energy. By combining advanced technology, strong partnership, and a strong commitment to the community we serve, we are creating models for building resilient energy infrastructure that benefit both people and the planet. Long-term view EGS technology. For decades, Ormat has led the world of geothermal energy, making it a reliable and clean source of power. Today, we stand at the forefront of the next revolution. We are not joining a trend, we are leading it our way. With a deep engineering approach, unparalleled experience, and the best partner in the industry, for us, EGS is not experiment. It is the next logical step in the evolution of geothermal energy, the way to make it available everywhere for everyone. We are not just talking about the future, we are building it. Enhanced Geothermal System, EGS, represent the next step in the geothermal energy. By using advanced drilling and reservoir technology, EGS can unlock 20 times more geothermal capacity by 2050. Ormat is leading the way with partnerships like SLB and Siege Geosystems, as well as targeted investment in the next generation geothermal solution. With EGS, geothermal energy can become a reliable power source in almost any region worldwide. Ormat in Taiwan. Taiwan is already on its geothermal journey, and Ormat is proud to play a role in this transformation. We are involved in key projects such as Gold Mountain, Lianzapin, Shuanzapin, Qinshui. This example of geothermal development driving Taiwan transition to cleaner energy and greater independency. By working together, we can ensure Taiwan maximize its geothermal energy potential while balancing modern development with environmental preservation. Now back to Hawaii with PGV achievement. PGV has accomplished a remarkable milestone, powering 25,000 homes, cutting Hawaii resiliency on oil by 190,000 barrels annual, investing in local community through royalty to native Hawaiian community, and measure to protect them from natural disaster. We believe geothermal projects should focus not only on energy but also on community engagement, providing transparency through public meeting and educational outreach while ensuring cultural preservation. 38 megawatt PGV achievement and collaboration with native and local community. Building trust is essential to operational success. Investing in health, educational, infrastructure, and local community. PGV story timeline. On 1993, 25 megawatt under construction with Hawaii Electrical Light Company, ELCO, based on Ormat equipment. On 2004, Ormat acquired PGV, investing millions of dollars to enhance plant efficiency, environmental safeguard, and community relation. On 2012, the production capacity was increased to 38 megawatt. It was recognized for reduction carbon emission and supporting clean energy goals. On 2008, Kilauea volcano eruption occurred. Facing the eruption, a race against time. In 2018, the Kilauea volcano erupted, threatening PGV's operation. In just 48 hours, Ormat shut down systems, evacuated hazardous materials, and worked with local authority to ensure public safety. Lava eventually destroyed wells and equipment, but our commitment to Hawaii never wavered. Ormat absorbed 75% of rebuilding costs beyond insurance coverage. By 2020, the plant reopened and is once again powering homes. This resilience shows how geothermal energy can overcome even the tougher challenges. One of our local team members said, preparedness and expertise saved everything we could. I would like to invite you to watch the following movie which shows what our local team encountered with.
It began in early May 2018. Kilauea, active since 1983, began a months-long eruption on the Lower East Rift Zone, which went on to produce 1 billion cubic yards of lava. Lava that transformed the landscape, covered roads, and inundated some 700 homes. In the wake of the eruption, Puna Geothermal Venture found itself entirely surrounded by lava. While the facility was largely spared, wells and transmission lines were compromised and our facility was inaccessible. When it was fully operational, Puna Geothermal Venture provided 31% of the island's energy. Without geothermal, there has been an increase in the need for fossil fuels and an increase in energy costs for both residents and businesses on the island. But the future is looking bright. We have already begun to forge a new path to get us back to where we were. Working closely with our oversight partners, we have designed, engineered, and begun clearing a new path to our facility. And with the help of the Kapoho Land Development Company, we are also in the process of creating access for our neighbors who have homes to the east of our facility. This is a project that all of us at Puna Geothermal Venture are proud to be able to fund and execute in support of our nearby community. Final details are wrapping up and we look forward to welcoming these residents home very soon. To Governor David Ige, Mayor Harry Kim, Hawaii Electric Light Company, and all of the local businesses and our community members that have stood by us during this unprecedented event, we can't thank you enough for your support. As we look to the future, Hawaii has mandated that 100% of the state's energy must be renewable by the year 2045. At Puna Geothermal Venture, we look forward to being a positive community partner and doing our part in making this goal a reality through safe, clean, dispatchable, renewable geothermal energy. Mahalo from Puna Geothermal Venture.
From recovery to restoration, a promise fulfilled. Instead of walking away from the damaged site, Ormat chose to rebuild, observing 75% of the cost beyond insurance coverage. The plant reopened in 2020, once again powering homes and reducing carbon emissions. Ormat also supported the community by volunteering, donating, and investing in local infrastructure, showing its strong and long-term commitment to Hawaii. Resuming power generation and signed a new PPA that enabled us to sell 46 megawatt, while today we are generating 30 megawatt. Repower PGV while reduce footprint and increasing efficiency based on Ormat comprehensive improvement advantages, such as enhanced brine handling system, power plant automation, scalability and grid integration, advanced turbine technology, post-2018 eruption optimization, environmental friendly operation, data-driven resource optimization. Ormat solution and expertise paved the way to unlock Taiwan geothermal potential. As we look ahead, geothermal energy is not just about reliable power. It's about people, it's about partnership with local community, respecting traditions and working together towards sustainable solutions. Hawaii's success can guide Taiwan and other regions towards cleaner energy, lower cost, and independency. Thank you for listening, and thank you again to the organizer for allowing me to share this story. Let's continue to work together to build a future power by collaboration, innovation, and resiliency.
So let's welcome James from the MTO New Zealand.
Okay, good morning everybody. My name is James Creed. I'm a technical director at New Zealand. Oh, sorry. I'd like to start with a voice of my admiration for the conference. Yesterday was very insightful, and the number of us attending both yesterday and today suggests that, to me that Taiwan geothermal is an exciting industry to be involved in, and we look forward to helping you with your developments. I'd like to thank the TIGC for the opportunity today, and thank you to my fellow delegates for coming along and listening. Hopefully what I've got to say and what MTL have got to offer may be of interest to you. If it is, then please come and talk to me afterwards, send me an email, and we can talk further. So the purpose of our presentation today is around steam gathering systems. We've had a lot of talk so far through this conference around conventional and EGS systems. I've picked conventional systems to talk about today. As we're all aware, geothermal projects can be quite complex. They differ significantly from thermal engineering, such as coal or combined gas turbines. And that's primarily because our fuel source is not constant, it's a variable. It varies depending on the quality of the well, dependent on the geology, and it will vary over the lifetime of the plant. And so what is important for us is that we must manage that resource actively, and we must design for it, that variability up front. So when we invest our capital at the start, we must be cognizant of the fact that the process conditions we start with may not be the same process conditions in 5 years, they might not be the same process conditions in 10 years. And equally, as we develop our power stations, we know we're going to have to drill make-up wells, we're going to have to drill wells to add to our re-injection, and we're going to have to work over those wells. And so those are all aspects that need to be taken into account of our design. So I'd like to talk through 5 items today. So first off, we'll spend a few minutes talking about an introduction, system overview, then we'll talk about some of the key challenges in steam gathering systems, and then we'll talk about the optimization strategies that may or may not help. And then we'll talk about some case studies and results, and finally we'll wrap it up with some key takeaways. So, first off, I think you probably mostly know this, but just for clarity, what is a steam gathering system? Well, it consists of these main items: the production wellheads, the two-phase pipelines, the separators, steam transition and scrubbing lines, brine re-injection lines, re-injection wells and pumps. And all of these elements are present in these systems, and they will differ depending on what your system and what your geology looks like. So, as a schematic, we'll rearrange those same things into the process flow. So we've got our production wells, we've drilled our hole in the ground, and we've got our fluid. But we've got to take that fluid and we've got to take it to our power plant. So typically, we'll take it to a separator and we try and separate the brine from the steam. Then that brine and steam, in some cases we would take it to an ORC, and that would probably apply to many of the projects you have in Taiwan. And then equally, we take our steam and that obviously goes to the power plant. Once our brine has come through our power plant, or possibly not if the temperature is too low, then we need to put it through brine pumps, most probably, and into re-injection wells. So this whole system, the efficiency of this whole system, of all these individual components, defines the efficiency of our power plant and defines the amount of power that we generate. So then the question is, why does optimization matter? Well, optimization matters because all of the losses, we look at pressure losses, heat losses, separation and efficiency, and parasitic loads. All of these have an efficiency associated with them. And if we don't optimise that efficiency, then we don't get the maximum power generation at the end. So the key point here is that a 5% improvement in gathering efficiency on a 100 megawatt plant can recover 3 to 5 megawatts of additional generation capacity. So what we're looking for is we're looking for that extra 3 and 5 megawatts that are free. They're there to be taken, and you just need to design your system to achieve it. So we'll look through several challenges first. So we'll look at the cost of pressure drop. And it might seem very simple, but we're thinking about the size of our pipes, the length of our pipes. So we can all understand that a larger pipe diameter means lower pressure drop in our system. But we also know that a smaller pipe means a lower capital investment at the start, but we will see a higher pressure drop and therefore a reduced turbine output. So the economic reality of this is that a 1 psi of pressure drop equals about 0.5 to 1% reduction in your turbine efficiency. And so as a developer, part of that balance that you need to strike is, do I want to spend more upfront and achieve more generation, or do I want to do a project in which I invest the minimum amount at the start, but I will see a penalty throughout the operation of that plant? And you need people that have done this assessment before to help you make those right decisions. So this is a graphical representation of this. We've got the lost revenue here is the mustard coloured line here, and we've got the analysed cost of pipeline capital cost. And what you can see here is there's an optimal position to be in, and that's what every project must go through and the assessment that must be made as you look at your steam governance. We come on to challenge number 2. So this is the geochemistry, the scaling and corrosion. And for you guys in Taiwan, and we obviously know that pH is a big challenge for you. So we've got these mechanisms. We've got the silica, the calcite, and the sulfate scales that occur. We all know that they are going to block our pipes. They're going to scale our heat exchangers. So therefore they're going to reduce the efficiency of both the pressure. You're going to increase your pressure drops. You're going to reduce your heat transfer coefficients. So we want to make sure that when we design our plant at the start, we're conscious of these things. These things will happen, and so we need to design for them and put strategies in place to deal with them. We come on to two-phase flow, challenge number 3. Two-phase flow is something that's always been an issue for geothermal, or consideration in geothermal. It is something that makes us stand apart from lots of the oil and gas applications. So there's a number of things that we need to consider from a two-phase flow perspective. Slug flow. We know if we've got pipes, we form a full liquid slug in that pipe, and steam will push that slug through, and it will create very large forces on your elbows, on your equipment, on your vessels. In the worst case, it will break these things. It will break the pipe, it will cause a loss of containment, and therefore it will save fuels. In the middle, you might get some vibration, you might get, which will therefore lead to fatigue loading, and you may see an early failure of the pipelines. So we don't want to see slug flow at all. Then we get intermittent flow, and this is where you get not a full slug, not the full diameter pipe filled with liquid, but part of the diameter filled with liquid. And you see the water rush through the pipe, and you get an intermittent loading of water. And this is what causes these irregular vibrations and fatigue loading. The wavy flow and the intermittent flow is most likely to occur where you've got uphill two-phase flow. And so where you've got challenging terrain, as you do here, where you're trying to build on the side of mountain hillsides, and you need to be considering, how do I lay my pipes out? Where do I put my separator stations? Because if you don't think through the route of your pipelines and the elevation changes, these problems are much more likely. So we've talked through the consequences, we've talked about this dynamic load on pipework. These dynamic forces, when you calculate them, are very high. We've talked about the vibration damage, and this can be just a maintenance problem where you're constantly replacing instrumentation, you're constantly replacing small valves because they vibrate and fatigue. Then we've got pressure oscillations, and these might affect your large vessels, your separators. And then we've talked about accelerated erosion at the elbows and changes in direction. So that's challenge number 3. So the key risk here is this point at the bottom here. Long uphill two-phase pipeline runs, they cause liquid hold up, and the inclination, the steeper that pipeline, greater the risk. So then we'll talk about the re-injection strategy. So depending on your plant layout, you might be fortunate in which you've got enough difference in elevation between where your plant is and your re-injection wells that the water will flow downhill to your re-injection wells without the assistance of pumps. That is the best possible outcome for you. If you do need pumps, then what we need to make sure is that those pumps are running efficiently, are sized correctly, and can cope with variations over the lifetime of the plant. So your wells will start to see a higher head pressure as they age, and they will require cleaning. So the basic equation is here is that when you start your investment, you can drill fewer wells for re-injection. But the problem with that is that you're going to see a higher parasitic load from your pumps. Alternatively, you drill more wells for re-injection, and you see a lower parasitic load. And so there is obviously an optimised position to be in where your drilling costs versus lifetime pumping costs cross over. So that should form part of any assessment that you do. So what are our strategies? We've talked about some of the problems, so what are our strategies to try to solve this? Well, firstly, we can look at well paid versus centralised separation. And this is much more applicable to the larger plants. It won't be applicable to your plants at, say, 2 to 20 megawatt size, but as you get above this, then these considerations will come into play. So do you separate your two-phase fluid at the well pad, or do you run those two-phase lines to a central separation station where you bring multiple well pads together and you have larger vessels? Both options are completely valid, but there are opportunities to look for saving capital costs and improving system performance. For the applications that you're likely to see in Taiwan, then we understand that you've got hillsides similar to those projects that we've been involved in Indonesia, where you have to consider the geography. It is a primary consideration in the layout of your plant. So I think this is a point that we make here, but it's probably not so important for projects using binary plants. But where you aren't going to use binary plants and where there is the possibility of using steam turbines, but we have to remember that the steam line and the need to make good quality steam before it enters the turbine is essential. And that comes down to the layout of the steam pipelines. So this graph is really just a demonstration of this point. So depending on where you locate the separator, whether or not you put the separator on your well pad plant, you have very short two-phase pipelines. If you put your separator at a distance away from your well pad, then you're going to have much longer two-phase lines. And what you see is a difference in pressure drop. And that difference in pressure drop, as we spoke about earlier, comes out in your balance sheet as a reduction in generation. And so it's important to understand these choices when you're designing your power plant. And that really comes back to that feasibility stage, to understand what are my options, what are the benefits and the negatives of each option, and which one gives me the best rate of return for my project. So hydraulic modelling and line sizing. Again, one of the key points here is that you have to look at your pipe sizing to make sure you're designing it both for the day 1 operation, but not only that, for the year 5 operation, the year 10 operation. Because if you don't get them right at the start, you'll see a second round of capital cost later on. And so our point here is really about, you need to make sure you have a good understanding of how to do those pressure drop calculations, what are the variables you need to consider, and that really comes back, from our perspective, that comes down from experience. Our correlations are built up over years of experience of real parts, and they aren't based on the oil and gas simulators. The oil and gas simulators aren't directly transferable to geothermal applications. And so those correlations that you see for two-phase flow, you need to understand the ones that are related to geothermal use. And this is a graph that sort of demonstrates the point about the need to correctly size your pipelines. So we know over time that enthalpy will decline, and so as enthalpy declines, you get less heat, and so therefore you get less power. And so what this slide is showing is that you can pick the lowest capital cost down here, but if you pick an optimal pipe size, then you'll see that here you'll need to start to drill up make-up wells. If you pick a more optimal pipe size, then you can extend the point at which until you start to see a reduction in deliverable megawatts. And that here in this graph is 13 years. So you're deferring your make-up wells for 13 years, so you're deferring that capital cost. So this slide is around the two-phase flow management. We've spoken previously today about the rough terrain and how you make sure you assess that terrain. And that's much more easily done now with 3D modelling, and we have tools to do that. We understand that we must control the flow regime. We don't want the slugging, because this is what's going to cause mechanical problems. So we need to understand how to lay out our pipelines with important configurations to avoid that happening. We need to make sure we manage this liquid, both in the steam lines and in our two-phase lines, to avoid these problems with liquid accumulation. And we need to understand the structural design. We need to understand what load cases your pipelines will see, and how you design your supports to make sure that those loads can be resisted. And that's as important around the seismic capability as well. Building pipelines that are resilient to seismic events. I'll skip over this slide because of the time limit, but essentially this is just a rough representation of what could happen in your pipeline. So we're looking around accumulation at low points, we're looking around these slugs that go uphill, and so your pipeline, as it traverses the terrain, it's important to make sure that those pipelines, these factors are considered in the routing of your pipelines. So we talked about geochemistry earlier and the risks that it poses. Well, the mitigations are about planning, understanding what your geochemistry looks like at the start of your project and what it could look like at the end. And so this is about when to apply the materials, when to apply the expensive duplex materials, and when are they not needed. And again, in terms of management of pH control of brine, you're trying to control on a triation curve in a very short band, where if you change the amount of acid that's being injected, then you slide up and down this curve very quickly. If you slide too low, we know we're going to have problems with corrosion. If we don't put enough acid into the system, we know we're going to be unsuccessful in controlling the silica dropout. So having the skills and the background and the understanding of how to do this is key to the success of your project. Again, I'll just skip to the end because I want to talk about the key takeaways. So pressure drop is a revenue concern, and so we need to make sure we size our project, our pipelines and our projects for the lifetime of the economics, not just day one. Geochemistry drives your maintenance burden, so we understand it and proactively treat it. Two-phase flow demands respect. The forces that it can generate are large. Separation philosophy matters, whether or not we're talking about a well pad or whether or not we're going to do it in a centralised location adjacent to your power station. That shapes your entire steam fuel system. Your steam fuel purity protects your turbine, and in cases of binary, protects your heat exchangers. And re-injection is often forgotten as not being that important, but it is essential because it has a significant impact on your parasitic load. So our message really is geothermal is not a copy and paste type of industry. Different reservoirs, different geothermal fluid, different terrain equals a different solution. It's about making sure you tailor your project to your environment rather than trying to copy and paste. You want to do a robust feasibility and auctioneering assessment, and this has been a point that's been made by other presenters. That is essential to make sure you put your project on a firm foundation before you move forward. And it's crucial to selecting the best solution. You want to make the right plan at the start, save time and cost in your construction, and then optimise your generation. And it comes down to that right plan at the start. And finally, there's a wealth of experience. I'm part of the New Zealand team that have come over to this conference, and we're very pleased to be here. But we bring a wealth of experience that we have helped other countries around the world over the last 20 or 30 years. And we're here to help you guys, as are the guys from Iceland. The geothermal community is a small community, and we stand by to help. So we are available to assist you to make Taiwanese geothermal a success. All right. Thank you very much.
Thank you, James. So our last guest, are you going to play the video or? Oh, very good. Yeah. Okay. So now we welcome Richard from MB Century. Good morning, everybody. We've all been sitting a while. This is the stand up stretch. I need a good idea. Just stretch up, put the bones down. This is time to take attention. The Kiwis are here. So just, nobody stands up. One man. He's paying me. Okay. So over the years, MB Century has developed some very sophisticated stuff. And hopefully this will go. Yeah, okay. So we live and breathe geothermal. The top picture here. Whoop, there we go with this. What have I done? Okay, push the red button. That way. Okay, pipelines are right there. Okay? The Wairaki power station is right beside us. So this is all casing, stacked, ready to go. This is our drill yard. We have fabrication, we have machine shop, engineering, reservoir services, and that's where I'm going to concentrate. And I hide over here. Okay. So, we do a range of services. We've been doing this 75 years, guys. Icelandic team here, just about as much. Well, actually, I think you started a fraction earlier.
on some things. Due credit there. But we perfected some techniques that nobody else did in the world, and that's what I want to talk about here today. So we do a lot of things here, and we have different partners. And as my friend James just said, the New Zealand team are here to help you, along with others. Okay? So due credit to everybody. We want to make Taiwanese geothermal successful. We want to make sure we're backing the people that are going to make the right decisions to make this work. So, we talked about drilling, we talked about research, we've got there, right? Now, everybody in this room knows that oil and gas is not geothermal, correct? Very good. We've got that across the line. Okay, during drilling operations, we don't get too sophisticated about this. We have some go rings to make sure that the well is clear. We make a pressure temperature spinner tool, and we run a few other tools just to make sure that we've cemented the casing in the right place. So this, and then when we do the well testing, very simple again, make sure the well is clear. And this is regular maintenance, guys. Pressure, temperature spills. High temperature casing, corrosion. So we talked about corrosion today. Your wells will corrode. You're going to drill in the mountain in this low pH. The casing will corrode unless you put in Inconel, which will be about 8 times the cost of normal casing. You've got to offset the value of all that. So, what's a go devil? I mean, in this room have been actually out on a job and seen something. 1 or 2 guys in this room will see something. But we make them out of aluminium these days. The reason that, if you get stuck down the well because of a problem, we can drill it out. You put it in steel, what's that going to do to a drill bit or machining tool? We used to make them out of brass, the old-fashioned ones, but it's actually cheaper to make them out of aluminium. And we want to run it because when you put the expensive tool down, a piece of aluminium, that's a couple $1,000. When I run down a special tool, you start at 85,000 US. So this is the $85,000 special. PTS tool. We design and build it in New Zealand because we live and breathe geothermal. We've designed the software system to go behind it. It's not adapted oil and gas technology. Okay? This is really special. And we sell these tools. Okay? So I don't know what's being run here in this country. I've been to several different sites across in my past 2 trips now, and I have not seen any T&P runs. So, what I'm trying to tell you here is that we sell a nice case, beautiful tools here, we collect this. This is all you need to do in data. Because we've had many years, we've got 75 years of records back in New Zealand, but here we've actually designed our software system here, so when the winch operator is running the tool down the well, he's getting this information live, and guess what? You can send it to the office here in Taipei, or you can send it back to New Zealand at the same time, and we can tell you what's going on. So, any questions? See, there's still people on the phone trying to find out who I am. I can see this. There's many people on the phone. See, got to keep an eye on you guys. Okay, so here, during drilling operation, we've involved this particular tool. We don't build this one, you can buy it. And this is here to help us figure out how much cement to put in the well. So, as you know, we're going to be drilling through some very fractured ground, very uneven holes, and we're going to have cavities behind the drill pipe when we're drilling. So, here, nice straight drill pipes, nice straight hole. Aha, we have a cavity in rough ground. And then here, this particular tool here can help us with these fingers up in here. They can help us determine how much cement to put in there. Cement is going to cause about 15% of your cost of a well, give or take, depending on the ground conditions. So, if you want to save some money, you're going to run a tool like this and use it correctly. But there's some different things in here. We can also find out the temperature here and help working out, because we're drilling into hot ground. You pump cement down, then it flashes off too quick, and you're not going to get cemented casing back to the surface. Why do we cement it back to the surface? A lot of blank faces here, guys. Oh, smiling in the back. He thinks he knows what's going on. Okay, so from there, if you don't have the casing cemented and secured in a well correctly, if water is in that cement, you're going to cause casing deformation. I've seen it happen in New Zealand. Believe me, we have made many mistakes. So I can go on a subject like that for hours, guys. But I want to make sure that you start to learn how to do this geothermal drilling correctly. And the whole room, everybody's been talking about this for 2 days. So we also have an ultra high temperature XY caliper. So we talked about the Geothermal before. This is the expensive version. This for here will give us up to 325 degrees, and it can tell us the casing, inside the casing, how much calcite's inside the casing. That's what we're trying to find out. Because you're going to have experiences, because at the moment you do not have a regulation that allows you to use anti-scalant chemicals here in Taiwan. You need to change the rules, guys, and this is going to come about by a bit of hard work and a bit of environmental monitoring and chemistry results, and really lobbying to grow this geothermal. Okay, so we put the casing in, we put the cement in, we worked out how much cement we're going to use before we put the casing in, and then we put in the casing, and we want to make sure the cement is in here. So we've got good cement down the bottom here, okay, and then the bad cement here. So what happens is the water in that bad cement, if you heat up the well too quickly, will boil. Natural reaction, same as boiling a cup of tea, building a cup of coffee. When the water boils, the casing will not go outwards, it goes inwards. I've seen 9 5/8 casing or larger, squash down, so I cannot get this microphone through the hole. So you're going from this size down to that size. You just destroyed a $7 million well on poor cementing practices, not knowing what's going on, or how you warm up the well afterwards. It's a skill that takes time. You don't rush warming up a geothermal well. You will destroy it. You need to allow it to breathe and crack and find its own natural state. You're working with nature, guys. You've got to work with it. You're exposing casing to 300 degrees Celsius in the good environments. We've seen more than that in New Zealand. In Iceland, they hit the jackpot, eh? Volcano flew. So they had to hold on to that baby. That was a challenge. And they did it safely. Without its own health challenges that they uncovered, but good on them. And that's a very important lesson there to when it goes bad. So they drilled into a volcano and it came back and bit them. We've been in different formations back in New Zealand, but it's different. Okay, any questions? I got scared you, everybody. Okay, so after drilling, we've done some other integrity testing here. So what are we doing? We're going to make sure that the casing is good. So we build a range of tools for that. And one particular tool will give us that data change here. In there, slight deformation of the casing caused by heat, stress, whatever's going on the ground. Earthquakes. We've seen earthquakes cause faults in New Zealand too. That can cause us issues. But we don't want casing collapsing, casing corroding. All these things here can happen. All very nasty. And they don't generate your electricity at the surface if you haven't got a good well. So this is a tool of favourites that we use in New Zealand. And I've actually had an inquiry from quite a few different countries overseas. I flew it into Mexico during COVID. It's been to America, Philippines, Indonesia, for example. But we run this tool every day. We build this tool in New Zealand. This tool can tell us if there's corrosion on the outside, between the casing joints. And there is an issue right there. But we've got 3 tools built into one. This here is a little tool that we make here, the round bit on the end. And in there, it gives us ID change. So this electronically, we can tell you if this inside of the steel is changing, moving smaller. In the center of this tool here, we can measure the roughness of the casing inside, but the primary is the phase change between the inside of the casing and the outside of the casing, and we can pick up corrosion on the outside of the casing at 280 degrees Celsius, a kilometre or more underground. So back here, we have the electronics in this part, and the centralizers to make sure the tool stays stable. This here is a casing joint, casing joint, casing joint. So we're picking up, and that is picking up about ½ an inch of thickness of steel. Now this does not give you an exact size difference of the inside of the casing, but it's an indication, and over time we can track. So what we normally do in New Zealand is we drill a brand new well, we've finished our completion test, we've done our warm up, and we'll run this tool and get a base load, because the drillers have told us that they put brand new casing in the ground. They said they put the centralizers on the outside of the casing at a certain spot. This is, that one there is the casing. That goes on the outside of the casing to keep the casing in the holes in the centre, so to make sure the cement gets up both sides all around the casing. Okay, so we can pick that up, but we can track where they tell us. When we picked them up, they said, oh, we put the X amount of casing collars in there, we add them up. Aha, you didn't, you took them and took them home for another guy. We tracked them down. We give them a lot of drillers a bit of a hard time, us reservoir services guys. But saying that, very important. We've seen in New Zealand wells from 5 years destroyed, eaten halfway through because of volcanic ground conditions have eaten through the cement and causing corrosion issues. And they've done a workover and then had to make a decision whether they're keeping their well. I was last week on a drilling pad with 6 geothermal wells on it, all producing. One right in the middle has got a corrosion issue. So how do they mitigate that? They're actually injecting condensate into the fluid, into the field to help neutralise the natural formation issues. So we've had to come up with all sorts of solutions. Okay, this tool here, only one in the world. It can do surface readout. Okay, we've got 60 fingers hiding in here. And one finger fell in a hole in the well that I was just talking about. And how we found that out was we did a drift run, very cheap, easy to do, it was clear. Why we picked it up, there was a subtle change in our monitoring of the well conditions from the operator. The operator said, there's something not quite right about this well. And what we found was that the fluid was going out through that into the formation. So over time we ran the drift, we ran the PTS with the spinner on it, and a little blip at a certain depth. And in this particular case, 220, no, my apologies. It doesn't matter, we found a problem. We've abandoned the well. But we went up in tool sizes and expenses. If you want to go really serious, you put a camera down a well. But you've got to quench it usually because they can only work to 150 degrees Celsius. So this tool here can work to 320 degrees, one pass, and we can actually open and shut the tool from real time. We figured out how to do that, and anybody else can make an electric motor work at 300 degrees Celsius, a kilometre underground. I give a new technical challenge to for technical people here in Taiwan. So, this tool here, we've used in the Philippines, New Zealand. It's a tool of choice. But, surprisingly, the EM tool, far cheaper to run, and it gives us that outside casing diameter, where this tool only gives you inside casing diameter change. That's all it does. But for certain people and certain operators in certain fields, that's what they would choose. Okay, we're getting there, guys. So, camera. Look what that camera's picked up. Here's a casing joint issue. Here, looking down here, we've got build-up of calcite, challenged it down the well. So it's quite a bit. But we do all these other services here, and tools. Okay, well warm up, clearing after workovers, well clearing, getting all the drilling cuttings out. Okay, before they end up in the separator or through the turbine and causing a lot of damages. That's very important. But during that warm-up session, we've worked out what the flows of that well is going to do. We might do a discharging run. Our friends before, from Iceland, my apologies, sir, had a very good example of a steam silencer with a weir box and a PT log being done at the same time, doing a discharging run, A1. So that was appreciated, to help illustrate to people in the room just what they're doing. But then we can also do acoustic formation imaging tools. That gets the geologists really excited. So we've got challenges with that. And then gyro, sometimes we need to find out where you've drilled to. Now if the driller has put too much weight on the bit and not had his hydraulics right, he can corkscrew the hole into the ground and cause a lot of issues. Instead of vertical or aiming up where the direction where the geologist said he was going to go. Seen it happen in New Zealand, seen mistakes, and you've got to learn how to do and get qualified drillers and people that understand how to operate their plant. Just like you know how to use your phone, your laptop in here, finding the right person that can use that expensive new drilling rig that you've just bought is very important. You must have a trained engineer who's available on site or available off site, but who's done the program to actually drill that well correctly, who understands the hydrology that's going to go on. You're going to hit steam pockets. We talked about it last night, that 200 metres down, hit a steam pocket, you come back over the rig in 15 seconds. Empty the whole well full of water, but fortunately the rig had a BOP on site. Very important, they're able to close it in and take control of the well. I've seen an accident happen in Japan a couple of years ago, and they drilled down onto a known geothermal location. There's geothermal, there's steam here. And then it blew out. They were lucky they didn't kill somebody, because it went twice the height of the derrick, and it was a triple. It was a big rig. It caused a lot of issues and abandonments, and guys, whatever you do with your geothermal sites, please do it safely, do it well, because every time you do a negative job anywhere in the world in geothermal, the news hears it, it's on your phones within half an hour, and somebody else is going to get a bad look, and geothermal is too small to be having bad negative effects. We want positive results. That's why the New Zealand team, along with the others from overseas, international companies, are here to help make this happen. So, guys, I thank you very much for your attention. Thank you.
Thank you, Richard. I think we can move on for QA. So if you have any question, please raise your hand and we will deliver the microphone to you. Anybody? Okay, so I think we are early. Let's call it a day, and if you still have the interest to move on to the other workshop, we still have time. So thank you for coming today. Thank you all.